Good morning, everyone. My name is Nathan. I'm a trainer here at SimpliPhi Power, and I'm joined by my colleague, Charles Holding. Chuck and I will get started in just a couple of minutes as we let participants come into the meeting. So welcome, everybody. All right, so it is 10 o'clock and today's training is on charge, discharge, and state of charge. So we'll be talking about how to know the state of charge, how to know what reserve is left in your battery, and how inverters interpret this information, and talking through some of the details that are there. If you'll give me just 1 second, I want to make sure that I mute my Vonage account. All right, so welcome everyone. We are a part of Briggs & Stratton. This training is an Elite IQ Installer training. You'll hear a little bit about our Elite IQ Installer program at the end of this training, and we're going to encourage you to join that program. We always start with a bit of a background, so you know something about our company's history, as well as our products. So SimpliPhi Power has been producing lithium iron phosphate batteries for the past 13 years, going on 13 years now. And our products are safe, proven, and simple. Safe in that we use a cobalt-free chemistry. We use lithium iron phosphate, so the iron is our metal there. So that makes them a lot less toxic and a lot safer for many reasons. Essentially, we don't have the risk of thermal runaway. This is a kind of unmitigated propagation of fire that you can see in lithium batteries that can happen when accidents happen. So these fires that you see are typically fires involving cobalt batteries. And because we don't use cobalt, we are a lot safer than much of the competition. Others are using cobalt, or others are using lithium iron phosphate as well, but we have a lot of certifications. We've been doing this a long time. We're one of the original lithium iron phosphate battery manufacturers in the US, a big player in the game. And we've gone through UL certifications, as we'll detail a little bit. We have UN Department of Transportation certifications as well, allowing us to ship some of our batteries. We're proven in that we've got over a decade of experience. We've been deployed in over 45 countries. We've got over 250 megawatt hours installed worldwide, and that number is growing rapidly. Early on in our time, we were approached by the US Army and Marine Corps and deployed batteries and tested batteries thoroughly for rough applications and deployment through the military. And so those are very rigorous demands, and we were able to go through their testing process and really realize the safety of lithium iron phosphate solutions, both in terms of optimizing generators and in providing mobile battery-based energy solutions for our military. We also strive to be simple. And what we mean by that is we want the install for our installers to go smoothly. We want to have everything kind of included as best as possible to make sure that we don't have installers taking a long time. So by being a simple solution, we are doing better at selling more batteries because our customers are doing better at installing them. We store energy for critical backup power. We're giving energy independence to people. The ability to have power on their own terms was our motto for a long time. We maximize resilience by basically giving people the ability to store power on site. And of course, we're helping to create savings for customers by allowing them to generate their own energy, store it, and release through time of use and peak shaving, on-demand charge management, etc. So at the bottom of the screen, you can see a number of our battery-based solutions. These are some of our products. Many people don't know that we have a high voltage division and a large projects division. And so if you have a very large project, we can assist with that. And so please message me afterwards. By the way, there is a Q&A, and so if you have questions, you can ask them in the Q&A. We will try to get to some of them. Chuck will try to get to some of them as I'm speaking. But if we don't answer that during the presentation section, during the slides, we will come to those at the end. And so we might be saving some of those questions for everybody to discuss together with us at the end. So please use the Q&A if you have questions. This is not a chemistry talk, but I'll just talk briefly about lithium-ion batteries. There are lots of different types of lithium-ion batteries, and they're typically categorized in terms of the cathode material. And as I mentioned, many of those many of those batteries use cobalt, which is a toxic metal and which has very questionable mining practices that are surrounding it. So we aren't using cobalt, we're using lithium iron phosphate. There is a need for other battery chemistries. Lithium iron phosphate offers a slightly heavier but more stable and longer lived battery solution. So know that there are lots of different types of lithium ion batteries when you're buying a backup solution for a house. And so for non-mobile applications, lithium iron phosphate, for many reasons, as I've mentioned earlier, is the best choice. But it's not just the chemistry that's involved, it's also how the battery is built. So on the right side of your screen here, you see cylindrical battery cells. These are typical cells like the AA cells that you're probably very familiar with. These cells this is called a form factor, how the cells are made. And these cells have many advantages in terms of durability, in terms of structural integrity, in terms of heat management. And so we use cylindrical cells. They last the longest of any of these cells, but they're a little bit more costly to make. There are also pouch cells for lithium, and you might be familiar with some of these. That's my hand holding an iPhone battery on the right side of the screen that had bubbled on me and split the iPhone apart. Now, this is probably 10 years ago now, but that's an example of a pouch cell. Pouch cells are the least costly cells. But they also are the most likely to go through swelling and contracting issues, which has the least amount of lifetime for batteries. Prismatic cells are typically very large cells that are made from rigid plastic cases, but they still experience swelling and contracting, and they have a little bit of problem with heat management. In terms of the cell being very large, it's harder to get heat out of these cells. And so they have a little bit shorter lifetime. So because of the advantages of cylindrical cells, even though it's slightly costlier, we use cylindrical cells in our battery manufacturing process here in Oxnard, California. So slightly into our products here, we have introduced a SimpliPhi ESS, that's an energy storage solution, or energy storage system, and this system consists of an inverter as well as a new series of batteries. These are 4.98 kilowatt hour batteries, so just under that 5 kilowatt hour need. If you have it, these are outdoor rated NEMA 3R enclosures, so these can be mounted on outside walls. They can be mounted outside. You have to pay attention to temperature, just like any lithium battery. But these are wall mountable. And so there's a mounting bracket that's included with both the inverter as well as these batteries. And these might be a good solution if you're looking for a bigger battery starting block for an install. We're going to talk a little bit about the Phi batteries as well. So this is our Phi battery has been a real workhorse, and it's installed all around the world. We have two different options for these Phi batteries. They can come in 24 volt or 48 volt options. We never run these in series, so you cannot take two Phi batteries and put them in series to get 48 volt. You cannot start with 224 and get 48 volts, so please never do that. If you need a 48 volt solution, start with a 48 volt battery. We only ever run our batteries in parallel. And this is so that the battery management system can adequately address balance of system needs. These are modular and scalable batteries. We do sell a wall bracket that can be used. We sell battery cabinets that can be used. And so we'll talk a little bit about those. These are a good battery for drop-in lead acid replacement. So if you've got somebody who's got an existing system, these batteries can be used with most other people's charging equipment. So you'll have to check the specifications of the charging equipment. But for many pieces of charging equipment, these batteries are a good drop-in replacement. You can come into a large lead acid battery bank and do a nice clean install with these 5 batteries. It's got an integrated battery management system to keep the cells balanced. It's got an integrated circuit breaker, so you can turn individual batteries off if you're in need of servicing them. And these come, as I said, in 2 different sizes, but both sizes offer 3.8 kilowatt hours of battery storage. The nominal voltage on these batteries is 51.2 volts DC. What nominal voltage means is when the battery's at a 50% state of charge, that's the resting voltage that you would see on the battery. And I'll get into that in a little bit. So if the battery is not running loads and it's at a 50% state of charge, the voltage you would see would be 51.2 volts. The amp hour rating of the battery is how many amp hours you can get out. This rating that is being shown right there, this is the SimpliPhi battery. That rating that's being shown at 75 amp hours, that's for 48 volts. The capacity of the SimpliPhi battery is 3.8 kilowatts as well. It looks a lot like the Phi battery, but you'll notice if you look at the top of the battery, there are these 3 communication ports. And so unlike the Phi battery, this has a communicating battery management system. That BMS offers temperature protection. It offers automatic set points for programming, and it gives communication through a gateway as well if you want to know information about the battery. This battery is a good choice for using with systems that require or need or will benefit from advanced communications. This is a UL 1973 certified battery. All of ours are. Max discharge. This battery is capable of, I'm sorry, that screen number is actually even lower than what it's capable of. This battery is capable of surging to 100 amps DC. In other words, this battery can put out, a single one of these batteries can put out 4.1 kilowatts for 10 minutes. So it goes up to 100 amps DC. The dimensions and weight, this is an 86-pound battery. It's just slightly heavier than the Phi battery. Same wall brackets can be used, same external dimensions on this battery. This battery is sold with our existing battery cabinets as well and can be integrated into our energy storage system. Closed loop communications help this battery communicate with, we have units that are approved with SolarC as well as our own inverter. We are still working on the process of reapproval with SMA. Limited to 72 of these batteries, so this is highly scalable. We've got a 3.8 kilowatt hour battery, that's your building block, but you can do up to 72 of these battery modules in parallel. And the limitation here really is the limitation based on the communication system. The communication system can do up to about 72 batteries in total. You're limited there by really the length of the Cat5 cable that you're using to connect the communication systems. This easily integrates with SolarC inverters. In fact, we sell SolarC inverters as part of a product ESS. They auto-populate the set points. They have high levels of protection and accurate readings in terms of state of charge, voltage, charge and discharge, temperature. There's even temperature control for charging slowly below 0 degrees Celsius. And so it also offers, having that smaller building block offers you very flexible sizing. It also offers you the ability to start out with a small system and build that system with time. So if you got somebody who wants to install maybe just a little under 8 kilowatt hours and start off with 2 batteries, they can always build that system up in the future as their finances and needs might increase. We have a smaller product line as well. This is our Phi battery that comes in 12 volts, a 1.4 kilowatt hour battery, much lighter. I think this is a little over 30 pounds. Yes, on the screen I can see it's 33 pounds, right? So this is an option for mobile solutions. A lot of people will use these for van conversions or for needs with even camping, that kind of thing. So if you're interested in this battery, it comes with either a 12 volt or 24 volt option. There is no 48 volt option on this smaller battery. 3/8 inch terminals there. It's got an integrated BMS, of course, to take care of cell management in terms of balancing. and it's compatible with most standard charge controllers and inverters. These are larger ESS systems. So we sell access cabinets with Solarc and Schneider inverters built in. We do all the programming in the factory and basically send this to you. And so we use the word plug and play because basically you get a system that's all ready to go. We are not allowed to ship the batteries installed, so they will come in individual boxes, but all you have to do is pop the batteries out of the box, wire them into the bus bars that are there, and this system already comes programmed and ready to go, easy to commission. So this makes for a very quick install. And the other nice thing about this battery cabinet here, it does offer you a little bit of temperature control as well. It can be insulated. It can come with integrated heating pads for cold weather solutions if you want that. That is a special order, but we can build heating pads into the units that are controlled directly from the BMS of the battery. This is a very quick install. It's NEMA 3R rated. It's ready to go outdoors, indoors or outdoors. Essentially no maintenance on these lithium systems, which is what makes them so nice. If you buy this with the SimpliPhi batteries, you have built-in communication. You can remotely monitor. If you buy it with the Phi batteries, you've got a slightly cheaper version, but you still have all those benefits of our long 10-year warranty on our products. Here's what today is all about: helping you to understand the charging cycle and the charging characteristics of these batteries. So I'm going to get into the charging cycle. All of our batteries are rated at a C/2 continuous charge rating. And what that means is that the capacity of the battery in 2 hours. That's how quickly we can deliver current to this battery, right? So if we have a 75 amp hour battery and we want to charge it in 2 hours, we would be limited to 37.5 continuous amps at 48 volts. Okay. Another way to think of this is if we're charging the full capacity of a 3.8 kilowatt hour battery in 2 hours, we're delivering half that, right, per hour. We're delivering half that capacity per hour. So that would be per hour. So this battery will charge at 1.9 kilowatts continuous. Okay. There is no surge for the charging cycle either. Now, because the 24 volt version of this battery has a larger total current rating, or sorry, a larger total, well, it really does have a larger total current rating, right? And so that battery will charge at a higher current, 75 amps DC, but it's still the same power because it's half the voltage. So we're still looking at 1.9 kilowatts for your charging equipment per battery. If you have 2 batteries in parallel, it would double. If you have 5 batteries in parallel, it would go up by a factor of 5. So 37.5 amps is the limitation for these most common 48 volt batteries. The smaller 1.4 kilowatt hour batteries charge, again, at half the total current rating of the battery. And so half of that 56 would be that 28.5 amps DC. And then for the 12 volt version, you're looking at that full 57 amps DC at 12 volts. So we have to make sure that if there are multiple charging sources running at once, that we keep these values in mind, right? So if you have a couple of SM80s, right, and you're going to be charging at 80 amps, well, a single SM80, right, is capable of charging at 80 amps. We need to make sure that we're not overcharging these batteries. And if an individual battery can only handle 37.5 amps, well, then we have to make sure that we have enough batteries in the bank. So that's what we mean by keeping these values in mind as you're designing systems. The other thing to tell you is, yes, these batteries have battery management systems. But really, this is not a fail-safe. The battery management system is there to protect the battery, right? But it's really the last line of protection. Proper sizing, proper design on systems is important when we're looking at protecting the battery. The battery management system's main job is to deal with balance of power and keep the battery operating properly. So it's important that we properly program equipment We want to limit the charge rate on various devices. So if we have a small battery bank that's undersized for our charge controller, we're going to need to make sure that the charge controller is properly programmed. Many systems now have hybrid systems where we have a hybrid inverter that's got the charge controllers built into it. And so we'll need to make sure that we set up the batteries properly and set up the charging rates properly. The SimpliPhi battery does have closed loop communications, but we want to make sure if you're using those closed loop communications, we have to make sure that the BMS, the battery management computer inside the battery, can properly communicate with the inverter. And right now, the two approved inverters for use with the SimpliPhi batteries are the SimpliPhi 6 kilowatt inverter and then Solarc inverters. AC coupled systems has further requirements. We have to be a little bit more strict on AC coupled systems. And the reason for this is that AC coupled systems are not easy to throttle back as DC coupled systems are. An MPPT controller on DC coupled systems can easily be set up to only allow a certain amount of current. AC coupled systems are basically on or off. If you've got an IQ8 on the roof, right, you're looking at 240 volts. That 240 volts is either on or off. And so when those AC coupled systems are used for charging, right, we don't have that same dial that we do with MPPTs. And so we have to be even more careful with AC coupled systems to always make sure that the ratings on the AC coupled systems are, that the batteries are sized as twice the number of kilowatt hours as the number of kilowatts for an AC coupled system. By charging characteristics. So, by charging characteristics, this is what a charge cycle looks like for a typical battery. So the charging cycle here starts out with a constant current. So let's suppose we have a battery that's mostly depleted. All right, sun comes out, it's charging off of solar, and so it's going to go through a charging cycle. That charge cycle starts off in what we call a CC, constant current process. Now that battery might start out at, let's suppose it starts out at around 50 volts. So the battery's charging cycle starts out at 50 volts. And as the battery starts to charge, the voltage begins to rise. So what you see here on the graph on the screen is on a vertical axis, you see the voltage of the charge controller. That's the thing pushing the charge into the battery. What you see on the horizontal axis is time. So what you're visualizing here with this graph is the charging cycle of the battery. You can see there aren't any numbers on the vertical axis, but you can see it starts off at a low charge rate or a low voltage, right? And that low voltage is going to charge, let's suppose we just have one battery, at 37.5 amps. So that's going to be a constant current. So if you look at the top graph here, it's of current, and current is going to be constant. How long is it constant? Well, until it hits the absorb setting in the inverter. And so the bulk charging cycle consists of this constant current process. Okay, so as that constant current is being pushed into the battery, as the battery starts to fill up, the charge controller has to apply more voltage to push that current in at the same rate. And so you can see in the bottom part of the graph here, you can see that the voltage is increasing as the current remains constant. And it keeps increasing until we hit a set point of the charge controller. And that set point is the absorbed voltage. After that point, we're going to keep the battery at a constant voltage. For our batteries, that setting is 56 volts. And we're just going to do that for 1/10 of an hour. And that's to top off the battery. So the bulk part of the cycle is the majority of the charging cycle. It occurs at constant current. As we get the battery to top off, we have to slow down the current rate. So the current drops off rapidly, but we keep that voltage at an absorb. And this should say 54 volts for 6 minutes. So sorry about that mistake there on the screen. So during the absorb cycle, right, it's going to, I'm sorry, it is 56 volts. During that absorb cycle, it is going to maintain a constant voltage for 6 minutes, which is 1/10 of an hour. So that's the typical charging cycle. There's an additional float process that can occur, and float occurs at 54 volts. And you would only typically float batteries if you have a renewable energy source where you're not paying for the fuel to float the batteries. And that's to try to keep the batteries off. So if you're using float charging, you're going to try to keep the batteries topped off. Okay, so knowing this, let's talk about the inverter capabilities or compatibilities. And one of the most important things is you're asking yourself whether or not you can use a lithium battery with old equipment is you have to ask, is it possible to set the appropriate charge settings into that charge controller? So can we get the appropriate set points? One of the set points is voltage. We want to make sure that we get that absorbed voltage right there at 56 volts. We also want to make sure that we can control the charging rate, right? And so that's the constant current process. So we want to have both of those settings there. It's also important that we don't use an equalize function with lithium-ion batteries. That equalize function in charge controllers is really built in there to provide a very high voltage to lead acid batteries to burn off sulfur that can accumulate on the surfaces. So we never use the equalize function of old charge controller equipment. That will damage lithium batteries. So you'll want to set that equalize time to 0 if you have that in older equipment. For AC coupling, we're going to absorb at 56 volts for 6 minutes. For grid charging, also same thing, 56 volts for 6 minutes. That's sometimes if you're setting in terms of an hour, that's 1/10 of an hour. And you also want to check maybe the system, if you're trying to check to see if the charge controller is going to work, make sure that the manufacturer warranties for lithium-ion batteries. Right? Maybe the system was just so old that it was designed only for lead acid and it doesn't have the appropriate set point for lithium-ion batteries. You'll save money in the long run. Batteries are expensive by first upgrading the equipment and then installing lithium-ion batteries. Okay, you can use external chargers if you have an issue where maybe the system wasn't set up properly and you have a battery go into a protect mode where it's been disconnected due to the battery management system shutting down and protecting the battery. We have a list of approved external chargers. These are chargers that you can use from an AC power source, just like a wall outlet, to charge battery banks up and top them off. So if you have questions about that, Chuck can answer those questions. And if not, we'll get to them at the end. Let's talk about discharge characteristics. So we just talked about the charging cycle. I told you it starts off at a constant current process, right? For our batteries, that should max out at 37.5 amps per battery, right? If you have 2 batteries in parallel, it would double to 75. The discharge characteristics are a little bit different, similar, but in terms of a discharging battery, our batteries are capable of surging. And so there's a little bit of a difference there in terms of discharging. So our batteries can surge for 10 minutes, and that's if you have a high output need. So let's look at a discharging curve. So if we have a battery that's fully topped off, the voltage of that battery is around a little bit above 53 volts, 52.2 volts is what's shown on the screen. Just keep in mind that that number does depend slightly on temperature. And it raises with temperature. So if you're starting with a battery that's at 40 degrees Celsius, then that starting resting voltage for 100% charged battery, the state of charge being 100%, would be just a little bit higher. And if you're starting off with a cold battery, it would be just a little bit lower. But here's what the charging cycle looks like. As the battery is discharging, you see that the voltage remains fairly constant compared to lead acid batteries. Lead acid batteries, AGM batteries have a much steeper curve here. One of the advantages to lithium batteries is that the curve is relatively flat. One of the disadvantages is because the curve is relatively flat, small changes in voltage can mean a big difference in state of charge. So as we look at the state of charge, at 100% state of charge, we're starting about 53 volts, right? And Still at around 53 volts, just a little bit less, right? We're looking at 70% state of charge, okay? And so it stays relatively flat. We start to get some drop-offs as we get to lower states of charge. At 30% state of charge, you're down about 52.2 volts, right? And then we get to the end of this discharge cycle, and after you hit about 10%, the voltage drops off really quickly. We call that location the knee. Notice at the top, I've labeled this graph resting open circuit voltage. This is the voltage that the battery would read if it was not powering loads, if there was an open circuit condition, right? I want to make clear here that the voltage of the battery bank depends on two things. It does depend on the state of charge. To a small degree, that depends on temperature. But for the most part, it depends on state of charge, right? As well as internal voltage drop due to internal resistance. So if you're discharging the battery or charging the battery, the voltage of the battery will appear different than if it's in a resting condition. All right, so look at the simple circuit diagram I've drawn on the right side of the screen. This simple circuit diagram shows a battery which is at a resting voltage of 52.4 volts. That resting voltage indicates that 52.4 volts is at a 50% state of charge. Okay. However, if we close the circuit and we allow current to flow through a load, the actual voltage measured on the outside of the battery terminals, as indicated by the delta V there in the diagram, if we measure across the outside of the battery, we won't see 52.4 volts. Will we see more or less voltage? So ask yourself that. Will we see more or less voltage if this battery is powering a load? So as the battery is powering a load, because there's some internal resistance inside the battery cell, there will be a voltage drop inside the battery cell. And so when powering loads, we'll see less voltage across the battery than when the battery is resting. That's why if you turn an inverter on and immediately start powering a load, you'll see that the battery voltage will drop. This is the opposite when we're charging a battery, right? When we're charging a battery, we see that voltage rise and rise and rise, and it goes all the way up to 56 volts, even though the battery voltage, resting voltage at 100% state of charge is just over 53 volts. Okay, the next thing to note about what I just said is that the amount of voltage drop you'll see below the resting voltage of the battery is proportional to current. So if I have a certain resistance and I double the current, right, I'll double the amount of voltage drop below the resting voltage of the battery. So that's what I'm going to show you here. This is a loaded battery, right? This is a battery which is in different states of load. So a C/2 discharge rate is the max continuous rating for these batteries. When I discharge at a C/2 discharge rate, it means I'm discharging the battery fast enough to fully deplete it in 2 hours. When I'm discharging at a rate of C/3, it means I would start with a 100% state of charge battery and I would fully deplete it in 3 hours. So it's a little bit less current for C/3. When I'm discharging at C/5, that means it would take 5 hours to fully deplete the battery. So the capacity of the battery in 5 hours, right? Notice that those are 3 different currents. C/2 is the most current being drawn out of the battery to power loads. C/3 is next, and then C/5 is the least. So if I look at these graphs, the discharging under load voltage of the battery starts out right around 53 volts, indicating 100% state of charge, 0% discharged, right? But then, because of the loads, the battery voltage will drop down. Notice that for C/2 discharge rate, the battery voltage drops down to 52 volts fairly quickly. In other words, when I'm pulling the maximum amount of current out of a Phi battery or an SimpliPhi battery, the voltage will drop by about a volt. Now, I'm only giving you this characteristic for a 48-volt battery. Cut everything in half, and it's the same looking graph for a 24-volt battery. It's a little bit better for the 24-volt batteries because they have more batteries in parallel. and so you don't see quite as much of a drop because there's a little bit less internal resistance. So the heavier the load, the more below the resting voltage you will be. And so this fact is what makes it hard to determine the state of charge or the state of discharge of your battery bank while it's loaded. So if you want an accurate measure of what your battery bank's state of charge is, if you just stop loads and measure the voltage, you can use this curve here to figure out what the state of charge is. But if you're loaded, right, it's a little more complicated, and that's why voltage doesn't tell you everything. If you know voltage and current, you can use this graph, and all of you will get a copy of this presentation afterwards. You can use this graph to figure out what your state of charge will be. And most inverters and charge controllers have the ability to keep track of this information now, and they'll give you a state of charge indicator. If those are not properly programmed for your battery bank, if the inverter is not properly programmed for your battery bank, it will give you an inaccurate state of charge reading. Keep that in mind. Okay, as I mentioned at the beginning, there is a slight temperature variation in lithium iron phosphate battery cells depending on temperature. And currently, one of the things I'm doing in my house here, and sorry, my video feed is so bad right now, I've got the sun coming out. One of the things that I'm doing in my house is I have a student here who's doing her senior project at the local university, and she's doing temperature-based cycling of lithium iron phosphate battery cells. And this is essentially what the battery cells look like at a very low load as you discharge them. This is essentially a resting voltage of a single lithium iron phosphate cell. Notice, if we discharge it at really low temperatures, -18 Celsius, right? I don't encourage you to do this, but if you discharge a battery at really low temperatures, look how much lower the voltage is, right? It's about half a volt lower than when you're discharging at 40 degrees Celsius. There's not a big variation between 25 degrees Celsius and 40 degrees Celsius, but a cold battery has less energy in it, or it can give less energy output because the voltage changes. And this is known as Poickert's law, and it's related to the output of a battery. So there is a temperature variation, so do keep that in mind as your batteries vary. The overall voltage for a fully charged battery pack will be a little higher at higher temperatures. Okay, go back into talking about Phi batteries and discharging characteristics. Batteries are rated for a C/2 continuous discharge. C/2 continuous discharge for Phi batteries, that's our 48 volt and 24 volt Phi batteries, is 37.5 amps for the 48 volt version. The 24 volt version is 75 amps. That's per battery. So if you double the number of batteries, you double this rating, right? So if I have 4 batteries at 48 volts, 4 3.8 kilowatt 48 volt Phi batteries, I'd have an ability to discharge at 150 amps continuous. Okay. So the other way to think of that is it's 1.9 kilowatts per battery. Our smaller battery, of course, has a smaller discharge rate. The current ratings, which are given to you there, are 28.5 for the 24 volt and 40 amps for the 12 volt. Notice, of course, that when you half the voltage on the Phi battery and go to the 24 volt battery, you get twice the current. Same amount of power output on both, right? Power is current times voltage, so both are capable of 1.9 continuous kilowatts of output. The surge on the Phi batteries, the surge is 80 amps DC, and it'll do that for 10 minutes. On the 1.4 kilowatt hour battery, you're looking at 60 amps DC for 10 minutes. For the SimpliPhi battery, you actually get a little bit of an increase because the SimpliPhi battery monitors temperature and protects those cells even better than the Phi BMS does. So the SimpliPhi battery, you can get 100 amps DC, right, for 10 minutes. So it's 100 amps at nominal, 48 volts DC for 10 minutes. In terms of residential use, we have a lot of use of the Phi batteries for grid-tied backup as well as off-grid. The SimpliPhi batteries being increasingly common for use in ESS systems, especially for people that want to be able to remotely monitor. Let's talk a little bit about protection. So I just gave you the safe continuous discharge rate, and I just talked to you about the surge rate, the maximum rating that any of these batteries can give at any point in time. So how do we protect the batteries so that we don't over discharge, right? Using inline breakers, as I'm going to show you in the next few slides, is not really the safest way to protect your batteries. It's not a fail-safe. Systems need to be programmed and sized according to the specifications of the battery. So I'll go into why. You can use breakers in line with battery banks. Of course, these have to be DC rated breakers, right? So there's a difference between AC and DC rated breakers. And you also want to pay attention to the AC output of your inverter. So if your inverter is a 10 kilowatt inverter, you should be able to figure out how many batteries you need to continuously deliver 10 kilowatts. 5 batteries would just be one too short, right? 5 times 1.9, right? We'd be a little bit under. We'd be at 9.2 kilowatts of power coming out of the battery bank, so you would need 6. So that's an example. We can go through more if you'd like in the Q&A. AC output of the inverter is important, right? Look at the max continuous output of the inverter. Even if your customer tells you, hey, I'm really not going to use many loads. Well, once they realize that their solar energy is coming in for free and that their inverter is powering loads, they start plugging in extra equipment and using energy more. My boss tells me that energy demands from customers always change, right, once they start using renewable energy. So keep in mind that you need to size based on the output of the inverter, not on what your customer tells you they're going to plug into the wall. Okay, so let's look at a breaker.
You mentioned the Q&A, so I wanted to jump in real quick and say there's been a bunch of good questions. I'm saving a couple for some lively discussions at the end. And I want to remind or advise attendees that we cannot have you speak. So if you're raising your hand, you got a question, put it in the Q&A. The webinar format does not allow attendees to actually speak. So your voice will be heard in the Q&A if you have your hand raised.
Thank you, Chuck. Appreciate that, and I appreciate the questions coming in, and I'm happy to go back through slides too at the end. Chuck and I will stay as long as needed to answer all questions. So please do add them there. We apologize that we don't have a method of allowing you to speak. Let me jump into looking at DC breakers. So first thing to mention to you is that there's a lot of variation in breakers. So when you see 60 amps on a breaker, your immediate thought is that, oh, the breaker's kind of like a fuse. If I hit 60 amps, it's going to flip, right? A fuse is going to burn out, a breaker's going to flip. But I want to point in mind that that's not instantaneous, right? So this breaker comes with a specifications diagram, right? And notice that if we look at the rated current of this breaker, 60 amps, and we look at going at 60 amps, right? This breaker will actually pass 60 amps continuously, right? It's a weatherproof outdoor rated breaker at 60 amps. And if you pass 60 amps through the breaker, it's not even going to trip. So where does it trip? When you get a little bit above 60 amps, it can trip. But look at the time on the horizontal axis. If I'm only about 10% above 60 amps, so suppose I'm approaching 67, 66 amps, it's going to take 500 or more seconds for this thing to trip, right? If I hit 125% of that load, I can see here that 125% of 60 amps, that's 15 extra, that's 75 amps. It's still going to take 100 plus seconds to trip, over a minute. So some damage could happen if you're relying on breakers, right, to protect your batteries. And even at 200% load, so this breaker will pass 120 amps, right, for 10 seconds before shutting off. Okay, so keep that in mind as you're sizing breakers, and each breaker is different. Here's another breaker, and you get this time graph as well. This one should trip, right, after 1.5 seconds, right at 100 amps. So when you buy breakers and you're using them to protect equipment, it's important that you look at the specifications on the breaker itself. This one, if I hit 200% of the required load, it doesn't take 10 seconds, right? It takes about 0.4 0.4 seconds or so, right, for this to do it. And this is on a log scale on the bottom. So it's a little bit different looking at this one. But again, check the specifications of your breakers as you're looking at them. Just like you would buy a fast blow fuse to protect your ammeter, you want to do the same kind of things to protect your electrical equipment. Here's an A&L fuse. It's a 60 amp rating as well. And you can see at 60 amps, this thing will never trip. Keep this in mind if you're using these things to protect your equipment, right? You have to get to almost 140% of load. And even then it's going to take 20 seconds or so in order for this fuse to blow. Okay, let's talk a little bit about the knee. The knee is when the state of charge of the battery is rapidly apparent, right? When you hit the knee, so that's when the battery is almost fully discharged, you'll see a very rapid drop off in the voltage. It's really not worth squeezing that last 5% out of your battery. Even that last 10% of the battery, you're not really getting that much more energy, right? You might get 0.1 extra kilowatt hours, but the battery is most susceptible in low states of charge. If we cycle a battery, if we take a battery and we cycle it from 100% state of charge to 0% state of charge, from 100% state of charge back to 0, back and forth like that, we're only going to expect about 3,000 cycles out of the battery. If we change that such that we're only dropping the battery from 100% to 20% state of charge, yes, you're losing a little bit of battery capacity there, right? But we expect 10,000 cycles out of that battery if you limit the discharge to 20% state of charge. If we limit it to 10% state of charge, I think the number is 6,000 cycles that we're expecting. So 10,000 cycles, you know, if that's daily, that does, if you do the math, add up to 26 plus years. And 100% depth of discharge, 3,000 cycles, you know, we're looking at more like 10 years. So you can get a lot more lifetime out of the battery if you limit where you cycle it to. So let's talk about, again, the knee here, right? So that knee is when you see a rapid drop off in the voltage, and that voltage of the battery, as we could see from the graph, starts to drop very quickly and it becomes very apparent. Additionally, heavy load at low states of charge is another added burden on the battery. It's really hard on the battery to have a heavy load when you're at a very low state of charge. And there's a physical reason for this, and it has to do with the density of charge carriers within the cell. So when I say density of charge carriers, I'm really just talking about the lithium ions. When a battery is 95% discharged, right, you have very few charge carriers left to carry the current. So if you're demanding a large amount of current, that means those charge carriers have to move that much faster. And so it's much harder on the battery. You get a lot more heat production at low states of charge when you're discharging at heavy loads. So keep that in mind. It's not a good idea to surge the batteries when they're down to 20% state of charge. Okay, low battery cutout effects. So basically, when you load a battery under a low state of charge, the internal resistance is increased for the reason I just told you, low density of carriers. And so instead of seeing maybe a voltage drop, right, for a surged battery of 1 volt, you might see a voltage drop of 2 volts because the internal resistance of the battery changes with state of charge. That being the case, if you try to surge a battery at low state of charge, the battery might do a low battery cutout, right? Or the equipment might do a low battery cutout because the actual voltage of the battery, even though it's above 48, that 0% number, the battery is seeing a large drop due to the load. So that's the internal resistance I was talking about. So you're more likely to, if you heavily load a battery, see low battery cutouts at low states of charge. So if you want to get all of the energy out of your battery, you have to do it slowly at the knee. All right, so set points. We encourage using a low battery cutout on your equipment of 50.2 volts. And that 50.2 volts will leave 20% state of charge remaining in the battery. If you're heavily loading batteries, you can use a slightly lower low battery cutout And that'll just prevent the inverter from shutting down when the battery actually has a state of charge of more like 30% or 25%. So if you have questions about that, we can go back through that. Let's talk about state of charge on the charging side of things. So resting state of charge. So if the battery is resting, your state of charge can easily be obtained from the graph. If you have a load connected, it changes. I'll come into that. So there's some real world expectations, and then there's some controlled testing voltage points, right? So when we control the temperature of the battery cells, right, it's more easily predicted what the state of charge is, right? And so when a battery is going through charging or discharging cycles or load, it's a little bit harder to tell. You can get battery monitoring equipment that helps with this. Like I said, the SimpliPhi already does that. We have a very advanced BMS inside the SimpliPhi, and it can give very high level state of charge readings, especially if you have a communicating inverter like our inverter, or a solar inverter, or even we do sell equipment. We sell gateways which can give all this information to you. So a gateway is a piece of equipment that plugs into the communications of the battery, and through software, you're able to read individual statistics off of each of the SimpliPhi and the larger SimpliPhi 4.98 kilowatt hour batteries. So with those communicating batteries, we can get more information out of them. So this is the battery voltage versus the discharge capacity. So as you look at your battery, right, under load, these are the various voltages that you can expect depending on what your load is. So if I've got a 2 kilowatt load per battery, that's a C/2 discharge rate, 1.9 kilowatt hours per battery, right? These are the voltages I can expect to see when the battery is loaded. So notice when we get down to a voltage of 50 volts, right, there's still 12%. There's still 12% capacity remaining in that battery. If we were discharging at a slower rate, you would hit all the way down here at 50 volts. You would hit 5% remaining. So that's what I was talking about. If your battery's under heavy load, you hit that knee a little bit quicker. So I'm going to be passing this information out to you through providing you the slides, and I'm happy to answer more questions that you may have. There is a correlation between that state of charge and the battery voltage, but that depends on loads. I want to mention to you as I close about our elite installer qualification program. So we have a program where you go through some training with us. If you're an experienced installer, we have you take a simple test. We'll even walk you through it. And we have an elite installer package where we're going to give you some perks for signing up and registering with us. One of the things that we do is we put you on our map. So if customers are reaching out looking for installers that are highly qualified to install our batteries and they search their area, you'll appear on that map. Currently, we're giving you a $25 cash back per battery that's installed. We also have a new promotion on the way where we're about to start next month. We're about to start a $500 bonus for signing up for this program. Again, the program is free. We'll drive some business your way. You get included in our Elite IQ newsletter. So we'll be sending you that newsletter. Gives us information, helps us provide promotions as well. But also you might be able to be featured in that. So if we select your company, we might feature you as a featured installer. Maybe you send us one of your photos. We'll feature you, and that goes out to thousands of customers and other installers around the country and around the world. So I'd like to encourage you to contact us if you're interested in this program. We have a photo contest. We've had one in the past. I think we're moving towards doing some other promotions this year, and so things are changing quickly. But again, I want to highlight this link for you. So it's going to be coming through the slide deck when I'm sending it to you. If you're interested in signing up, you can also just give Chuck or Daniel or I a call, and we can help you through that application process. Another thing to point out to you, since you're on the front lines doing the installations, all of the specification sheets, the manuals, we even have integration guides on our website. So if you click on support on our website, we have a lot of product documentation here. So suppose you're interested in installing our equipment with an Outback charge controller, or maybe a Schneider inverter, and you want to know the settings for that inverter. You don't have to call Schneider or Outback. We've already done all of that work for you. We go through an integration guide where we talk about using our batteries with other people's equipment. We've got some how-to videos on there as well. And then if you've installed a SimpliPhi battery for customer, register your warranty with us. Send us some pictures of that. We might even feature those pictures and provide some recognition for your company in our newsletter, as I mentioned. So all of these things are available on the website. It's pretty comprehensive. So again, we'd like to thank you. If you have additional questions other than the ones we're about to answer, email us at training@simpliphipower.com. So thank you, everybody. Let's jump into the questions, Chuck.
Yeah, I got some good ones here. I tried my best, Nathan, to knock them all out, but they kept coming. And there's definitely some discussion items. Starting off the top, Briggs & Stratton is based in Wisconsin. Are there any plans to establish manufacturing of SimpliPhi in the Midwest? I don't know.
That's a great question. For right now, our plans are to continue the manufacturing in Oxnard, California, at our factory there, and our production offices there. But yes, there may be changes in the works. I'm not privy to them.
That was about what I thought too. A wire sizing question came in based on if we should be sizing for surge. For example, the AmpliPhi's got that 100 amp surge, or maximum continuous discharge rate. And
that's a great question. And if you don't mind, I'll take that, Chuck. Yep. So in terms of the ampacity of wires and wire sizing, right? We helped somebody do this the other day, right? So when you're sizing your equipment, oftentimes the battery bank is capable of surging to more power than the equipment can handle. So if you have a piece of equipment that is only going to be able to output a maximum of 6,000 watts, you can size this. You can size your wires based on the max load that your inverter can handle, or so the max draw out of the batteries. It's often the case that people are looking for longer backup, right? And these batteries are capable of huge amounts of short-term power draw, right? But oftentimes your limitation is the inverter equipment. So my recommendation is, if you have a small battery bank, you have to size it based on the batteries. But my recommendation is to look at your equipment and see what the max load you're going to provide on the batteries, and you can save your money by sizing according to what your equipment is able to draw out of the battery. So if you have an inverter that's capable of surging, right, to 200 amps at 50 volts DC, right? That would be 10,000 watts. If you have an inverter capable of surging at 10,000 watts, size your wire, right, based on the inverter's draw out of the battery bank. And always keep in mind
some efficiency there too. So not only the 10,000 watts on the AC side, but if we have a 93% efficiency, we need to tack on 7% because that'll be being pulled on the DC side.
Good point, right? So I think that, my answer to your question is look at how much you can continuously draw out of the batteries, even if it's a surge, right? And you can size based on that. There's nothing wrong with doing that.
Thank you.
But pay attention to the surge and, as Chuck said, the inefficiencies. So look at the maximum that your equipment can draw. Remember, that's on the DC side of things. So it will be drawn at nominal 50 volts, right? All right, next question.
Daniel had asked earlier about compatibility, and I advised, as you had stated during the presentation, that Solarc and SimpliPhi ESS were the only ones that we had closed loop communications established with at this time. He had a comment about Schneider. I am in line with him. Schneider's a great company, very reliable. Do we know? I don't know if we know a timeline for when a Schneider closed loop communication might be.
I don't have a timeline either. So the answer is yes. So first off, we do sell systems with Schneider. We sell access cabinets with Schneider. Schneider is a great company. And we are in the process of getting our communications batteries to meet their communications protocol for their inverter. But until our BMS can talk to their inverter, I can't recommend that you use SimpliPhi batteries with the Schneider yet. You can use Phi batteries, right, as long as you program those set points in with Schneider. And that's what we sell. We actually sell the Schneider inverters with our Phi batteries as part of our access plug and play package. But as of right now, we don't have the communications worked out, and I don't have a timeline for you. I'm sorry, Daniel, but great question.
Another question, I'm not quite sure I understand the question. What about the DC rack level high-speed DC fuse?
Yeah, I think he's talking about fuses for high voltage racks, but I'm not quite certain of that. Yes, there are better fuses, there are better breakers to use. My highlighting of breakers there was just to point out to everybody as they're sizing battery banks that the breakers aren't perfect, right? And that breakers, even though they're rated at a certain rating, can take a while to trip. Even the same thing with fuses, right? You guys are probably all familiar with fast blow or slow blow fuses, right? Where, you have a difference in the amount of time, and that time can matter to some pieces of equipment, can be pretty sensitive. So I'm not sure, Shiv, about your exact question there. But you kindly suggest on the peak let-through current of fuse to be evaluated in case installation of the battery energy storage system rack level. I'm not sure your exact question, so if you want to clarify and send us an email, we'll be happy to try to answer it. Okay, next question seems to be from Mike.
He's asking if we have I believe if our BMS is out there for developers to use. And I believe the answer is no, that it's proprietary, right?
Yes, we have a proprietary BMS that we write the software for, and unfortunately, we do not have a developer package there. Can you get temperature and voltage info to use in your application? Absolutely. You just need to purchase a gateway, and the temperature, voltage, state of charge. I think the SimpliPhi battery monitors temperature in 16 different locations. So you can get access to some of this stuff through a gateway that we sell. So the gateway is a piece of equipment that communicates directly with a battery BMS, and you can get individual battery information that way.
And that would be from our closed loop communication capable batteries, the
yes,
SimpliPhi.
The SimpliPhi 5 kilowatt hour battery, exactly, 4.98, yes. Drew is asking, I assume cycle data is for all cycles to standard DOD. So if you occasionally discharge beyond 90% and mostly do 80%, then effect is minimal, right? But each 90% discharge is probably 3 times the effect of an 80%. That's exactly right, Drew. And we know that nobody is going to discharge the battery to exactly the same depth of discharge each time. It takes hundreds of 100% depths of discharge to really do damage on a battery cells, right? And so the occasional 100% depth of discharge is very little effect, right? Even at 100% depth of discharge, you're still looking at 3,000 expected cycles, right? So, and we give you a 10-year warranty at 100% depth of discharge. So it takes thousands of cycles to really do damage. I recommend that you try to cut them off at either 20% or 10% state of charge, just because you'll get that much more expected life out of your battery. But however you decide to use it, we give you a 10-year warranty. Timothy Albaton asks, is our product available in Nigeria? Yes, in fact, we do have a distributor, a seller that works in Nigeria who I've interacted with a couple of times. My wife is also from West Africa, so I know that we also have some products available in Ghana and had people interested in them. And yes, there is a seller in Nigeria that sells these products. And so if you send me an email, I can put you in touch with him, Timothy. Kelly asks, What is the shutdown voltage programmed into the Phi BMS? And the answer, Kelly, is 46 volts is the low battery cutout of the Phi, which the Phi will go into a protect mode. So the battery itself will shut down. John Valentine asks, we'll be there, and I think you were asking for low voltage. There's also a high voltage, which I believe is 58 volts. But I'm not sure. I'd have to get back to you on that if you were interested in the high voltage cutout as well. Okay, so Sheev asks again, during charging, state of charge of battery will suddenly jump from 85% to 99% state of charge. And while discharging, it jumps from 25 to 1% or less, due to which BESS system is not working and is in standby condition. Can you explain? Without the details of your ESS system, it's very hard for us to know. As I mentioned, some of the inverters, especially if programmed wrong, will not give accurate state of charge readings. And again, the only ones that are currently approved for use with our SimpliPhi batteries are the Solarc and our SimpliPhi charge controller. We previously had approved SMA batteries, but we were having some problems after they did a firmware update. John Valentine asks, will there be a load center to accompany the Briggs inverter charger? Sure does make it easier to install these units. I'm not sure on the product release map, John. If you send me an email, I can put you in touch with somebody who might be more in touch with what products are going to be released. Timothy asks, with battery cutoff set, is a breaker still needed? No. The answer is no. As long as you size your system properly, you do not need an inline breaker, and we don't even recommend one, right? Because of the inconsistencies in breakers that we mentioned. Ned writes, hysteresis setting, uncontrolled phenomena or setting to set? I'm not sure, Ned. I'm not sure how to answer that question. So hysteresis has to do with when you cycle a battery, you don't necessarily get back to the same starting point that you started at due to different effects. So one effect would be temperature, right? So if I cycle a battery from 100% down to 0% state of discharge, and then I charge it back up, instead of reaching the original voltage, I'd actually be at a slightly higher voltage, right? Because the battery is at a higher temperature. It's different for different battery chemistries, but that's one effect. And I don't know about the hysteresis setting. So I think I would have to dig deeper to be able to give you any kind of qualified answer, Ned. Is there a stabilization time before using voltage to determine state of charge after removing current sources / sinks? We don't have a specific recommendation for stabilization time, Ned. What will happen after a battery charges up is the temperature will gradually come down. And that's one of the reasons that people will hold it in a float cycle, is to really make sure that you're at 100% state of charge depending on your temperature. But we don't have a recommendation on how long that might take, and it would really depend on environmental considerations. Matthew writes, I feel like I'm avoiding a lot of these questions, so if you guys want to dig deeper, feel free to email at that email address on the screen. Matthew writes, the ampacity of output conductors for the ESS shall be not less than the greater of the nameplate rated circuit current indicated on the nameplate, or the rating of the ESS over current protective devices. Right, so our particular ESS system is a 6 kilowatt continuous, but it's capable of surging to 12,000 watts, right? And so based on that, the ampacity of the conductors should be sized based on our ESS system. So note, I think Matthew is trying to answer other people's questions there too, that the ampacity of the conductors shall depend on the nameplate rated circuit indicated on the ESS system, and for us, that's the inverter. And he gives the SEC code there for that as well, NEC code for that as well. And so we appreciate that reference. Nazaf writes, we have a telecom customer that requested fire suppression system for lithium ESS. What do you recommend for SimpliPhi ESS? We do have a detection system that we use. I'm blanking on the name right now. Chuck, do you know the name of the system we use in New York?
I don't.
So Nazaf, if you get back to us, we have a monitoring system that we actively sell and program for you, and I can get you that information. If you send me an email, I'll connect you with our engineering team that can provide you that information. Okay, I appreciate your attendance. And if you have further questions, feel free to email us at training@simpliphipower.com. Again, thank you for your time and attention today. Please stay tuned for future trainings. Have a great day.